Recording. Hello, everyone. My name is Abdullah. I'll be moderating this meeting today. Please know that this meeting is recorded and will be uploaded to YouTube. Please adhere to Kubernetes code of conduct for public meetings. So today is August 4th. We have a presentation about kubeflux by Claudia. Just before giving the mic to Claudia, I would like to announce that we have a batch day in KubeCon North America in November. So I'm just going to paste the call for papers on the chat. The deadline is August 8th. So please, if you have something to present, even if it was presented in the past, but you have new, new ideas, new features that you added to whatever system that you're working on, or features, please feel free to submit a proposal. Last time it was the first time in Europe. I think it was a very successful one. We had a lot of good discussions. So I encourage everybody to submit a proposal. Hopefully this one will be even bigger because typically the one in North America, the event is bigger than the one in Europe. With that being said, I'm going to give the mic to Claudia to discuss and present kubeflux. Claudia, I think I need to make you a co-host to present.
Yeah. Okay, I'm able now. I hope I'm showing the right screen.
Yes.
Is that good? Okay, thank you so much. So hi everyone, I'm Claudia Misale. I'm from IBM Research in Yorktown Heights, New York. I will be presenting today some work that we are doing around scheduling mainly, but in general in running HPC workloads on Kubernetes. The other main person behind the project is Dan Milroy from Lawrence Livermore Lab. And he's online now. Just saw him despite it's very early. He's in Pacific time, so thank you for joining. And there are other people behind the project, Red Hat, IBM, and Livermore. So it's quite of a large group. So I was following the template for the presentations for this meetings to the batch SIG, and so I tried to stick to that as much as I could. It's not a lot of slides, but hopefully we'll get to the point. So for the first slides were about motivation and Kubernetes gaps that we are facing while we try to run those HPC workloads. So for this applies also to AI workloads, I would say, but for now we've been just running traditional HPC workloads. Those are like molecular dynamics simulation, linear algebra, Monte Carlo simulations, and all old school stuff. They are all MPI workloads, at least the ones that we've been running. So lately, we've been exercising the some of the workloads in the Coral 2 benchmarks. Those are the benchmark needed to be run for the pre-exascale computing supercomputers acceptance, so for the Coral systems. And so we've been building those in containers and run them on both AWS, EKS, and OpenShift on IBM Cloud. So these are MPI workloads. They can be either the one that we've used. We had a mix of network intensive and compute intensive. To enable the MPI workloads, we use the MPI operator from Kubeflow, which we changed a little bit, but this is not the place where to talk about it. So those workloads basically require to have an MPI-enabled Kubernetes cluster. For what concerns the communication patterns, so that's again all old school MPI communicators. And so we can have a mix of reduce, all-to-all communication, stencil computation, nearest neighbor, scatter. So any possible combination of communication that can be happening in any MPI application, that what we would usually get into the traditional HPC workloads. Another requirements, of course, is having group scheduling to run these workloads, because these are MPI. We all know you need to have all the pods being up at the same time before you can even start the computation. Another feature that is preferable is having topology awareness while you place the workloads in the cluster. So you want of course that depends also on the kind of application that you need to run. So some can have they have different requirements. So if you have, for instance, an application that is more like network intensive, maybe you want to put them closer to each other so that the network is not doesn't cause big problems or slowdowns in the in performance. And having also topology, knowing the topology of the cluster where those applications should run can help the scheduler, if the scheduler is topology aware, and to make better decisions for to place the workloads. Some may or may not need exclusive use of resources, so you may need to have like an entire node for a workload, or you can just have require exclusive use of part of the node, so like set of CPUs, you want that to be exclusive use for a certain workload, so you want to share or not share network interfaces. And another thing that we that's something that, of course, like in traditional HPC, when you run traditional workloads on traditional HPC on-prem clusters with some job scheduler, so Slurm, LSF, to name just like some famous names. You need those kind of give you the consistency of the placement. So if you have a certain set of requirements, and unless the cluster is being allocated to other users, etc. But in general, the feature of having repeatable and consistent results when you execute those workloads, that's something that is a feature preferable in Kubernetes clusters. That's the main topic. So given all this list of requirements, we move to the list of gaps that we are identifying while testing those applications on Kubernetes. So of course, depending on the application that you run, you need to have preferred different placement algorithm for the application. So for instance, if there is a application that is more compute intensive, then maybe you want to rather spread the pods in the nodes so that they can have a better use of their resources and do not interfere with each other. So having a way of saying, like, if I would like to use like a pack or spread, just to name something that is familiar to everyone, that's something that is not immediately available in Kubernetes, but we know that there are ways to improve scheduling with having more schedulers with the scheduler framework. And another thing that it's in the requirements, and that is sort of a gap, but there are tools in Kubernetes that help you to fill the gap about topology awareness in scheduling. So there, in the node objects, there are a set of labels that we can use to define more topology aware when we want to allocate the workloads in the cluster. So for instance, we have the region and zone labels, and those can be used to make a more topology aware scheduler. Of course, the scheduling, of course, the topology awareness can be more or less detailed. So you can go from like region, node, zone, and node. So that's like a 3-level topology that you can define, but then you can also go farther in details in that. So you can go socket or NUMA aware scheduler, like the NUMA aware scheduler plugin. So there are different level of topology awareness that you can specify. Some are there, some can have to be done by who is implementing some more features. One thing that we have faced when trying to run those HPC workloads was to so we little context. So we try to use the default scheduler as best as possible, to the best of our abilities, and use all the possible features that are available in Kubernetes. So like we did really extensive use of affinity, especially at the zone label level. But this works up to a certain point. So if we want to get an allocation on certain nodes that belong to a specific zone, if you have a cluster that spans over multiple zones, and you want to make either I wrote there exclusive use, but can be also shared. That doesn't that does apply to both scenarios. So in an example that's probably the easiest way to explain what I'm trying to say is that, for instance, imagine you have a Kubernetes cluster that spans over 3 availability zones. So you have certain number of nodes per zone, and you want to do like a pack placement or on just 2 zones out of 3. In that case, with Kubernetes, how you would do is in the pod or deployment YAML file, you would specify that those pods need to land on nodes that have availability zone 1 and 2. So the workload will land on these 2 set of nodes. This works, of course, but the thing that wasn't enough for to make those workloads perform well was the fact that even if you have the ability to select 2 zones out of 3, the pod placement was not good enough to make the application perform given the application requirements. So for instance, if we want to have a pack placement for the workloads into those 2 zones, once you select the 2 zones, the default scheduler would place either node in any zone in any of those 2 zones randomly until if the nodes are empty, of course, and until the resources then are all full. With the need of having a plugin or a scheduler placement that does packing is that you would fill one node in one zone first, then you fill up the entire zone 1, and then you go to zone 2. So that's a gap that there's something that we were not able to do with the default scheduler and the affinity labels that we were given. And that, of course, then is like a side effect that grows in complexity when scaling, when having large clusters, because if you can rely in a small scale with affinity or taints toleration, but you have to basically do that by hand in the YAML files. At the larger scale, this becomes more and more of a burden on the user. So if the scheduler could do whatever it does and solve that for you, that would be easier on the user perspective, but also the application would perform as well. Also, for the last point, that's kind of mixed with the one that I've been just talking about. So having also a predictable and consistent allocation of the pods when we have these certain types of work, because this doesn't apply, of course, to all the workloads, but in this specific HPC area, having the same placement consistent, and especially if you're running workflows and not just one application, but multiple HPC applications that build a workflow, having a consistent allocation of the pods, that also guarantees that the application have consistent performance. And oh, sorry, there's a typo. That should be a P. And also we also had experienced when deploying the workflows that the fact that given an empty cluster and trying also to take advantage of affinity, and anyway, the group scheduler, when the resources are all the same to it, it will randomly pick a node among the sets of the nodes. And this may impact also the startup time of the entire application and the application of workflows. And these, of course, then impact the overall performance. And yeah, so we've been experiencing this these gaps, and we let me move to this. And so since we are in the business of scheduling, so we've implemented this scheduler plugin that is called kubeflux, and this is based on a Flux, the cluster management and jobs scheduler system that's implemented and maintained by the Livermore Lab. For any further question, Dan can definitely help out here since he's the Flux expert. So, but I will try my best. So the Flux is big project, has several components, since it doesn't do scheduling only, but so it also does cluster management. So for this particular work, we are using Fluxion, that is this scheduler component in the Flux framework. We use it, we build that as a shared library that we use from the scheduler plugin through a Golang binding that we implemented, so it's quite straightforward. One thing that it's very useful in Flux is that the representation of the resources of the cluster is graph-based. So the good aspect of this is that any placement that Flux does with any of the placement algorithms that are available in the library are automatically topology aware, and the topology of the cluster can be more or less detailed depending on the labels that are available in the node objects. For instance, if the cluster is like a cluster running on a cloud deployment and like on VPC that spans over multiple availability zones, that label is present in the node object, so we can take the information and build a cluster that also has the level of topology awareness at zone level. We can go in more fine-grained details according to what is available and that we can implement so that we are kind of Kubernetes compliant, in the sense that we're not trying to inject artificial or our own labels into the node objects, because we want this thing at least to work on any Kubernetes cluster. So we use whatever Kubernetes gives us. And we can go even in more details using the node feature discovery operator that is implemented and maintained by by Red Hat, and that also gives more information about the hardware on the nodes, GPUs. So we also, if that's deployed in the cluster, we also collect the labels that are created by the node feature discovery operator and attached to the node objects. And we build the cluster, the graph-based representation of the cluster, also using that information. So it can be more or less detailed depending on what we can find. The side effect that is a problem that we are leaving unsolved on purpose is that having an internal representation of the resources, that means that the kubeflux scheduler has an internal state that is maintained. And this is because it will make placement decisions based on what's available in that graph of the resources. So it's like a graph matching algorithm that is executed every time we need an allocation of pods on the cluster. So is not bidirectional in the sense that Kubernetes always knows all the pods that are created and are executed and allocated by kubeflux, but is not true the other way around. So kubeflux has no idea of what else is happening in the cluster. We decided not to go through the let's say pain of implementing state consistency. Because it's a complex problem to solve. To have the best use of the cluster along with kubeflux, it's needed to have to let Flux manage a certain set of nodes. So basically, you would need if it's better if the default scheduler or any other scheduler would not use the same nodes as the one that are used for kubeflux because of this state consistency. About how this is implemented. So we are using the scheduler framework for that. And we are implementing two of the extension points, the pre-filter and filter, where in the pre-filter, that's the point when we issue the allocation request to the Fluxion component, which runs as a sidecar container in the kubeflux pod. So we have two containers. One is the scheduler plugin, and the other one is this gRPC server that is a service container to the main one. And so the Fluxion library runs in the sidecar, or everything else is in the main container. This separation allows also better maintainability of the code because it's two different code bases. And so this simplifies also our lives in terms of maintenance. So we, to deploy this scheduler, so we basically follow what's provided in the scheduler framework. So for whatever works for any other scheduler plugin, that applies to kubeflux as well. The only difference is that we have the sidecar container in the deployment, but that's not compromising the deployment process. So of course it runs, no privileges are needed. We don't really need to install anything other than the pod group custom resource definition that we use for group scheduling. We didn't want to reinvent the wheel, so we use what the community provides us, and that's just been working perfectly great for us. And so to enable group scheduling, you would need to do that as you would do in the co-scheduling plugin, if you're familiar with that. Otherwise, Kubeflux would just implement a pod by pod placement. So yeah, as I mentioned in the previous slides, there is no state consistency guarantee. So the nodes should be dedicated to Kubeflux. As any other scheduler plugin, you would just name the scheduler name in the YAML file of the workloads that are to be deployed, and the installation is just a set of YAML files. It's just RBAC, a service account, config map for the scheduler, and a deployment file for the container.
Can I just interrupt quickly here? Like we
Absolutely.
have a few more minutes.
Yeah, that's the last slide. Is the last one. Yeah. Yeah, just last bit is that still not part of Helm install, but we'll be working on that soon. And that was the last sentence.
Thank you so much. We have, I think, about 10 minutes for, is it 10 minutes? Yeah, about 10 minutes like for questions. Anybody has any questions to Claudia? I have a few, but I want to give it to the community first, a chance to ask.
I have one also.
Go ahead, please.
So do you run like two different schedulers, one for optimize and working with Kubeflux and other default scheduler for normal workloads, or you just run one default scheduler in your cluster?
Oh, no, that when we ran our experiment, we were not removing the other overriding the default scheduler. So that would be just there, even because we use it to allocate the Kubeflux pod as well. And yeah, so it's not supposed, I mean, that's then on the user preference, but it's not supposed to be a replacement for Kube scheduler.
Got it. And another question is that do you do any work around by control the job release? I mean that, let's say the 10 jobs that come in, but Kube scheduler, you will release those jobs in its own way. But do you have your own priority model or some model by which you control, hey, I want this X job to release than others?
No, we're not managing any of that, if I got your question correctly. Are you talking like about queuing or doing preemption?
Yes.
Okay, so we're not handling that. So we have two options that we are looking into. One is to integrate the scheduler with MCAD, the multi-cloud app dispatcher, or with Queue, so that we like to separate the queuing mechanism that you would have in a batch scheduler system with the scheduler. So we want to decouple those two and integrate them. Another option is to use to integrate the queuing mechanism in the Flux framework and put that into, I don't know, like an extension of maybe MCAD or something. But we don't want to, we want to have the separation here.
Thank you. Thanks a lot.
Thanks.
Any other questions?
Yeah, I had a question. Thank you, Claudia, for sharing the implementation of Kubeflux. You talked a little bit about the gaps and the expressiveness of the job with regards to allocation restrictions or like across zones. How are you able to express that in your jobs, and how are you going about expressing that so that it can be mapped properly in the graph that's in Kub?
Right. So that's also managed by. So let me take back what I said. So we can that can be done in two ways. One way is just letting the scheduler do the placement based on the placement algorithm that's using. So what, for instance, we create the graph of the resources, and which has 3 availability zones. So if you select then to have a pack placement algorithm, Flux will figure out by itself that the subgraph within the first zone, that's where it has to go first. Then it will go to the other one. So at the user level, you don't really need to do anything other than selecting the placement algorithm that would fit better how you would like to the pods to be placed. Another way that we have enabled, but that can that's still quite simple. We had there's from the YAML file in the job that you want to run, we can specify that you want like exclusive use of a specific label, like it can be zone or node. So that if you specify that you want exclusive use of a zone, then that workload would again put into the exclusively into a specific subset of the graph that belongs to a specific zone, for instance. So you can do that in 2 ways, but the easiest and is to just let the scheduler figure that out.
Okay. Very good. Thank you.
Thanks.
Any other questions? So I've got one. Like you mentioned that the Kube scheduler doesn't support like packing and spreading, or like there's one of the gaps. But you could do like resource-based. Like we have a plugin that is basically tries to a scoring plugin that tries to either spread the pods based on node utilization or pack them. It's kind of similar to what you just described, which is basically a global policy, right? Like whether everything is going to get packed or
right,
we're going to spread everything. So you might want to take a look at that and see, like maybe tuning it might be helpful to achieve
sure.
some of these semantics. But like
yeah, I mean,
question,
spread and pack
yeah,
is not something that we invented. So it's, of course, depends on, it can be implemented in several ways. So we had that for free there. So yeah, but that makes sense what you're saying.
The other question that I have is like, at what scale do you run? Like, if every pod that you're trying to schedule, you're making a call out to Flux. I guess that I'm assuming that's what's happening, right? Like the plugin is basically making a call RPC or something to Flux. Is that a concern in terms of overhead latency? And how many pods do you expect to schedule per second? And how big is your cluster? Like, can you give us a sense of what your experiments scale were?
Yeah. So for the latency added when doing the gRPC calls. So far we really didn't have any didn't experience any slowdown in that. So it's in the order of milliseconds, if I remember that right. That's yeah. I hope that's what I remember is correct. So even having very like more fine-grained allocation rather than having large asking for a large set of resources. So having a burst of allocation requests that was always in the order of milliseconds. So that for the test that we've been doing some time ago, that wasn't an issue. The cluster size that we've been running lately is in the order of thousands of virtual CPUs. Then how large was your AWS cluster? I cannot remember the number of nodes, like 30 to 30 something, and the same for.
It was 32 nodes and 3,008 usable CPUs, but we've scaled much larger than that. That was simply for the MPI application testing. We did hello world testing at greater than 16,000 ranks. And as kind of a side note, that's a comment on the kubeflux scalability. The Fluxion component is designed to scale and does scale to exascale machines. So the scheduler itself is designed and will be used as the primary scheduler for the El Capitan machine, which is going to be an exascale class machine that comes out next year. So at that point, you're talking tens of thousands of nodes.
Right, thanks for adding that. And so for our tests, we went up to 3,000 MPI ranks in total on AWS and about 1,800 on the OpenShift cloud on IBM Cloud. That was just a smaller cluster. And yeah, it depends. We had different scale of resource requests from the application, more like smaller MPI worker or larger MPI workers. So that really depended on the workloads, but either fine grain or larger grain of resource request, there wasn't an issue there. Of course, whatever time it takes to Flux to get an allocation, then that time has to be put into the entire scheduler machinery that is behind the scheduler framework. So of course there's also that overhead, but that's what you get anyway. So we're on top of that, like baseline, we are not adding much. So that's been working good for us.
I think you mentioned that you run a lot of experiments with existing APIs, such as, I suppose, the pod affinity, node affinity, and so on. I was wondering if you use, first of all, if you use preferred affinity or you use mandatory or required affinity.
Go ahead, sorry.
Yeah, if you did prefer, did you tune the scheduler, or did you just use the default configuration?
Tune the default scheduler, you mean? Or which scheduler?
Yes, tune the default scheduler, but tune the weights of the scoring.
Okay, yeah, so for the preferred and the fixed affinity preferences, so for it depends on the workloads, but since we were running a workflow, so different applications, we had to force the use of subsets of the availability zones to make the affinity work good. And because with the preferred, then it would anyway span over the other zones if there were not enough resources. And for a particular application that was QMC pack, that's a Monte Carlo simulation, there was a problem for that application, because spanning over 3 zones, if 2 were not enough, the application would not complete, because it could not handle the latency induced by the fact that we're 3 different zones. So we were forced to put that into 2 zones at most, because otherwise it would not complete. So the preferred doesn't really work most of the time, even because if you do the preferred, then it's kind of like you're just at the end using the entire cluster, so you're not really doing affinity as you would like. That spreading over all the zones, that would work for the AMG workload, for instance. That's more compute intensive, so it doesn't really care about the latency. So the preferred in that case would work, but doesn't work for other applications. And either way, also having preferred placement, preferred affinity, then the allocation of the pods would be not like the pack or spread. That could not really always work fine. Spread, yes. Pack, no, because it would anyway do like a spread on all the zones. So it's really a matter of know your application, and if you know the application, then you know what's needed to make it work, and use the tools that you have. But sometimes that's not enough.
Thank you so much, Claudia. We're 5 minutes.
Yeah.
Which is great. People are interested in the project, asking really interesting questions. Thank
you everyone for the questions.
Thanks. So this meeting will be uploaded, and please, if you want to share the slides as well, we can post them in the meeting notes.
Yeah. How do I share the slides?
Just if you can convert them into Google Slides, and then you can just share a link. That would be probably the best way.
Google Slides. Okay, thanks. Will do.
All right.
Great.
Thank you, everybody,
Claudia.
and see you in 2 weeks.
Thanks everyone for the time.